Hi, welcome to the fifth lecture on compactness. Today we are going to continue with our study of compact subsets of a topological space. One of the most important thing, we are going to look at what kind of intervals will be compact or not compact. Okay, and later we will of course look at what kind of subsets of R will be compact or not compact. In fact, even in Rn. Okay, all right, let us get started. But before that, we will look at some one or two examples which are left over from the previous things. Okay. Or closed and bounded, not. Yeah. Right. I think I had already seen. I'm sorry. I'm just. I'm distracted. Okay. Oh no. Yeah. So we had already seen the following. If I take R with a lower limit topology, this is not compact. All right. Okay. Now let's look at any open ball BAR in Rn. This is the first example of today. This already seen. I wanted to do it, but then I remembered we already saw it in the first one or two lectures. Okay, this is not compact. Okay, many of you will remember what is called Haley-Borel theorem and try to say it's not closed and bounded, but you still have to prove it's bounded, but it's not closed, right? But I will give a very direct proof. Okay, remember, to show it's not compact, what should I do? I have to exhibit an open cover which it does not admit, of course infinite, yeah, which has no finite subcover. Okay, we are directly proving. We are not using any other characterization, as you most of you would know that. Okay, this is very easy because let us look at this. Okay, this is an open ball. Let us assume this is my A, right? This is my R, right? Choose n so that, okay, what do we want? R minus 1 by n is still positive. That means R is greater than 1 by n. Since R is positive, this is possible, right? Therefore, for every n greater than or equal to n, let us look at the open ball BA R minus 1 by n. So this is contained in BA R, right? And these are open sets. And notice that if you call this as UN, UNs are increasing. That's because UN is contained in UN plus 1. Next, I claim union UN equal to BAR. This is again by Archimedean property. By now you should be sick of this, yeah, right? Because R, yes, you start with any x in BAR, then distance between A and x is less than R, right? Therefore R minus distance between A and x is positive. Therefore there is an n so that R minus dAx is greater than 1 by n by Archimedean property, etc, etc. Yeah, I hope by now all of you know that. Therefore what I have an open cover, okay, an increasing open cover, okay, and it has no finite subcover. Why? Again the same trick. Okay, if, okay, as usual, by arguing, we had already seen 3 or 4 times. Therefore there exists some m, a natural number, so that my BAR equal to BA, the UM, that is BAR minus 1 by m. Why can't this happen? You will simply say R minus 1 by m strictly less than R. That's not enough. You understand that? So let us look at, this is my A, and yeah, this is, yeah, you are following? Yeah, now start with any one direction, for example E1 direction, right? Let's look at A plus RE1, and this is this is a line segment I'm looking at. I'm looking at the line segment A plus RE1. Yeah. Now notice that if I have any x, then x is of the form, all of you know that, a plus t times e1, where 0 less than or equal to t less than r. Yeah, I hope all of you remember what is a line segment. Line segment is a plus 1 minus t times a plus re1 minus a, that is a plus 1 minus t times re1, that is 0 less than or equal to t less than or equal to 1, but equal to r is not allowed, therefore t equal to 0 is not allowed. That's it. Are you following? Please pause, review, because these kind of things are never, you by intuition you just go ahead, but we are trying to prove everything. We of course start with geometric intuition, but we try to prove rigorously. So PRP. So is this clear? That's what you have to check. Okay, right. Therefore now what do I have? You have something like r minus 1 by m strictly less than r. Therefore if I look at r minus 1 by 2m, call this as a t, then a plus t of e1 lies in the ball bar, but it does not lie in the ball bar minus 1 by m. That's because it's distance between a and a plus r minus 1 by m, 1 by 2m, sorry, 1 by 2m. Yeah, this will be minus get cancelled, so you'll have something like r minus 1 by 2m. I hope I did it correctly. Are you following me? Sometimes I myself get confused. So a plus t1 minus a, this is t is positive, therefore t times, that's it. And what is t? T is r minus 1 by 2m, but that's not less than r minus 1 by m. A contradiction. Okay, so what have we concluded? I have concluded, okay, so this is the picture you should have. So if I have a and this, there are this, and those of you are watched some of my earlier lectures on cluster point, okay, you would remember this is the argument I gave. Okay, every x in BAR is a cluster point of BAR. Okay, so this was done in the video on cluster point. There also I would have said many people do not even realize. Okay, yeah, so we pause, review that. So finally what you have shown is BR, any open ball in Rn is not compact. Okay, the same proof goes through any or non-linear space. If you know what is a non-linear space, you can just go through the same argument. So this is true. Okay, it's not compact. Okay, good. Right. Now let's look at the third example. Let me take an interval either form this way or this way or this way or this way or this way. None of them is compact. Remember, there is always okay. These are all very easy because, for example, a infinity you can write as union a n greater than or equal to 1. All right. So this will be an open cover of this, which will not admit any finite subcover. If you want to be clear, I may have to start with n greater than or equal to a, because n may be 29. In that case, I have to start with from 30 onwards possibly. And so for this again the same thing. What will I have? I'll have minus n to a union. This will not admit a finite subcover. Now how will you deal with the AB? The same trick. This is the union of what will you do? Remember, I want an open cover, so if you want, I can also take this open cover. This is contained in, okay, so this is equal to a b plus 1 by n, the b minus 1 by n. So I am in a, this is b, and this is b minus 1 by n. Okay, as n varies, okay, so that n into b minus a must be greater than 1, otherwise it will be empty set. Okay, you are all MSc students. You already used this kind of explanations. I had already given why I have to choose n so that n into b minus a is greater than 1, so that this interval will be non-degenerate interval. It will be, otherwise it is still correct. It's an interval. It will be empty set. Remember, empty set is an interval. Okay. Yeah. Are you pause? Review. Proceed. Okay. Now let's go to one more example. Let us look at R2 with the order topology. That is dictionary order. Then we claim it's not compact. Because you would have already seen, we have shown that all these vertical lines x equal to a, if you call ua equal to x comma y, where x equal to a, this vertical line, these are all open sets in the order topology. And if a is not equal to b, ua intersection ub is empty, right? Therefore, if I get the collection ua as a varies over the indexing set R, now this is an open cover. R2 with order topology, and of course it has no finite subcover, right? If it has a finite subcover, there is a finite subset of f in R, right? A finite set. Then you start with any alpha in R but not in f, then u alpha cannot be there. For example, alpha comma 0 will be here, but alpha comma 0 cannot be in ua for any a in f, because if alpha comma 0 is in some ua, then alpha must be a, but a is in f, but I chose my alpha not in f. Okay, pause, review, proceed. Can you see the more general argument now based on this? Can you see a generalization of this? This argument? Suppose I have a topology space x tau, and suppose I have a partition, okay, is a partition of x by means of open sets, right? Therefore x equal to union ui, I in I, because it's a partition, this is correct, and this, therefore this also becomes open cover. Okay, this union shows open cover, right? Okay, right? Then what do you say? So if I is an infinite set, then x tau is not compact. Yeah, so those of you who have watched my earlier thing, okay, application is partition topology. If you had watched my earlier videos, examples of topology spaces, partition topology is one such, so that also becomes an example, right? Now we are ready for the main result of this set, but before that let me prove one lemma which is very useful. Let x tau be a topological space and be a basis for the topology tau. Okay, then x is compact if and only if every open cover of x consisting basic open sets, not all basic open sets, you understand that, admits a finite subcover. So let us first understand what the theorem says. Okay, the crucial part is I have a basis, right? This is the basis for the topology, right? Suppose I have a collection bi and I, so that for all I bi belong to script b. Okay, this is a collection of basic open sets. Okay, now this is a collection of open sets also, right? Suppose it happens x equal to I bi, then I call this collection, this is an open cover, right? I call this collection an open cover of x by means of or by basic open set. Okay, in any open cover, what we allow? We allow any kind of open set. Here in this, what I am taking is only basic open sets. Okay, you are fixing a basis. You follow that? And this is true for every basis also. Understand the subtlety, right? You gave me a basis script b. Somebody may give me a b dash, another basis for the same topology tau. Then I will say x tau is compact if and only if any open cover with the open sets coming from b dash, that also admits a finite subcover. Okay, whenever you read such a theorem, please stop. Do not simply get into the proof quickly. Okay, try to think what it tries to say. Okay, one way is clear. Which way is clear? If bi and I is an open cover by basic open sets, okay, if x is compact, assume x is compact, okay, let b bi be an open cover by means of a basic open, then bi is an open cover, right? Forget whether it's basic or not. And x is compact, therefore what do I know? There exists a finite subset I, so that x equal to union bj, j is an f. Therefore we have proved one way. If x is this way, I have proved if x is compact, okay, every open cover of x consisting of basic open sets coming from b admits a finite subcover. That we have shown. Okay, now converse. The converse is also equally easy. Okay, let ui I and I be an open cover. Okay, then what do I want to show? I want to know whether x is compact. What is the hypothesis for the converse? You have a fixed basis, and with respect to the basis, okay, you give me any open cover consisting of basic open sets coming from here, this admits a finite subcover. That is my hypothesis, right? So now you want me to prove x is compact. What now you are given me is, you are given me an open cover ui, but ui are not necessarily open. Sorry, basic open sets. So what should I do? Very easy. What will I do? I have to create an open cover consisting of basic open sets. Okay, this is how you have to learn to think. Okay, so what is the key idea? So we look for a basic open cover out of this cover. I usually don't write such things. I'm writing so that you'll try to understand this. I'm going slow for that reason, right? How will I do that? What does it mean to say it's a basis? This is a basis. You give me any open set here and give me any x in U. There exists a bx in script b, so that x belong to bx and bx is contained in U, right? This is the definition of basis, right? So now you have an idea, right? What will I do? Start with any x in x. Okay, since x equal to union b I in I, x belong to this x, therefore it must belong to one of the bi, therefore there exists I of x in I, so that x belong to, oh I'm sorry, I'm very sorry, so what I'm given is open cover ui, so let x belong to x, but x equal to union ui, therefore there exists ix in I, so that x belong to ui of x, right? Now this is an open set and script b is an open cover, sorry, it's a basis for the topology. Therefore what do I know? Therefore there exists a bx in tau, sorry, in script b, so that x belong to bx and bx is contained in ui of ix. You follow that? Right. Now let's look at each bx is a basic open set. It's an open cover. Why? X is union of bx. Because give me any x, it is in bx itself, right? Therefore this is a basic open cover. When I say basic open cover, what does it mean? It's an open cover consisting of basic open sets from the given basis, right? So by hypothesis, what do I know? There exists a finite set of x. Finite subset, so that bx x in f is a finite subcover. Do you agree with that? That's because of hypothesis, right? Now, but what I'm supposed to show? I'm supposed to show the given open cover ua admits a finite subcover. Therefore, I have to find a finite subset. So let us say a finite subset G of I, so that ui or uj, j in G is a finite subcover, right? How will I do that? That's very easy. Yeah, for each x in f, okay, there exists an ix, so that x belong to uix, right? Okay, now let's look at this collection uix as x varies over f itself. I claim this is a finite subcover of the given cover. Why? Because x equal to union bx x in f, but remember each bx is contained in uix, right? Therefore this is contained in union ui of x as x varies over f, but that is contained in x, therefore equality holds. Yeah, so pause, review, proceed. This kind of thing, you know, go through twice or thrice so that you don't have to remember. You will find it is easy. It comes automatically the way you have to think. Okay, and many of you, what you want to do is you go line by line and miss the thing. Okay, have confidence, go through it. Okay, just do not be happy just because you understood my explanation. No, just go through it again, then you will see you yourself can give the proof on your own. You don't have to remember. Okay, so now the main result of the section, this is the theorem. any closed and bounded interval in R with the usual topology is compact. Whenever we write R with no topology mention, it's always with usual topology. Proof. Okay, before I embark into the proof, let me tell you two things. First, okay, if you have time, okay, spend at least 1 weekend to read my article, the LUB, the role of LUB. You can download it from the usual place where I have already written that 4d space .mtts .org.in.ea for expository article. Okay, maybe I should write it carefully. Okay, and two, watch my video on the connectedness of AB. In both the thing you will see the proof I'm going to give for the compactness of closed and bounded under AB is exactly similar to the connectedness proof. Okay, all of them depend upon LEB property. Okay, so which is least appreciated, okay, by analysts most often. So let's start with the proof. So let UI be a collection, a basic open cover of AB. You remember what are the basic open sets in R with the usual topology? They are open intervals. So I am assuming my each UI is of the form AIBA. It is strictly not necessary, but it's good to assume. And next, what I am assuming, I am not going to assume my AIBA is going to be open in closed interval AB, because A has to be in one of the UI, right? So what I am saying is this is type 1 open cover. So it's a type 1 open cover, but each open set is also an interval. It's a basic open cover. Do you understand this? Okay, learn to think like this, appreciate. Okay, do not just jump to the proof. Okay, therefore what is possible, maybe my A maybe one AABA, similarly my B maybe one AJBJ. You follow that? And then need not be symmetry. Even though I have written like this, okay, my A may be here, BA may be here, my AJ may be here, and BJ be here. In that case, it's very good because one single open cover will do. Okay. So what is the trick? The trick is, let us look at A. A is in AB. Therefore, there exists a I such that A belong to AI BI. Is that clear? Yeah. Now notice that therefore A is strictly less than BI. Therefore I have AI BI and A is strictly less than B. Therefore there is a delta so that delta positive, so that A plus delta will be less than BI. Right? For example, look at the distance. Take the half of the distance between A and BI. The middle point of A and BI, that will be contained in that. Okay? You follow that? Okay. Okay. So now notice that therefore the interval A to A plus delta, the closed interval, is contained in AIBA. But that is your UI which is in the color or the open cover. Right? So now I form the set E which is set of all x in AB, so that the closed interval a to x is is covered by finitely many open sets from the open cover. That is, the closed interval Ax admits a finite subcover. So what does it mean? Let us again try to understand. This means there exists an fx, a finite set fx contained in I, such that my interval a to x is contained in union ai bi I in f of x. So as x varies, f suffix x. Okay, it may not be the same finite cover, right? If x1 and x2 are different, it may be different finite covers. These are the things you have to understand. Okay, because this kind of subtleties, if you had been taught at BS level itself, at master's level, I don't know to repeat. But the system being what it is, one has to explain all these things. Okay, are you following? So I claim this E is not empty. Why? We just now saw a plus delta belong to this, because a to a plus delta is contained in a single open set a bi. Therefore my f of a plus delta is a singleton I. Right? Okay, you follow that? Okay, now notice that for every x in E, x is less than or equal to b. Therefore b is an upper bound of the set E. Therefore E is a non-empty set and bounded above by B. Therefore by LEB property, there exists a C in R, so that C is the LEB of E. Right? Now few things we want to observe. What are the few things I want to understand? Remember, a plus delta by 2 belong to E and C is an upper bound. Therefore a plus delta by 2 should be less than or equal to C, but this is strictly then. Therefore I should have A is strictly less than C. Right? Next, B is an upper bound of E and C is the least upper bound. Therefore what is the relation between C and B? C is less than or equal to B. Therefore what I find is my C has to be somewhere here. Do you understand that? Pause, review, proceed. Okay, so what are the first step? First step was to form this, to prove there is a delta positive, so that a plus delta, a to a plus delta is covered by a single open set ui. And second thing is to form the set E is the second step. Third set is, and prove that this is non-empty and bounded above. The third thing is, let C be the LUB and then C lies in the interval A to B. Okay, this is how you should go through the proof, step by step. Do not get lost by the details. Each detail is very small, 2 or 3 line proof. Right? Okay, now I claim this is the second step. I am claiming C must be equal to B. Why? Suppose I already know A is less than C, less than or equal to B. If this is false, what does it mean? C must be strictly less than B. Therefore I have A, I have B, my C. Right? Now since C is there, then there exists some AJ, BJ, where J is an I, an open cover. Right? Now C belongs to this open interval. Okay, my CJ, BJ, let's just for fun, let me do that. This may be my AJ, this may be my BJ, or this may be my BJ, or this may be BJ, something. You understand that? what I want to say is, since C belongs to AJ, BJ, and this is an open set, AJ, BJ is an open set which contains C, therefore there exists an epsilon positive, so that C minus epsilon to C plus epsilon is contained in AJ, BJ. Okay, so let me write it. This is my epsilon neighborhood of C, and that's completely contained in, and so that this is contained in actually AB itself, I can assume. If by shrinking epsilon still further, I can assume C plus epsilon is less than B and C minus epsilon is greater than A. Are you following? By shrinking, so this is this, by shrinking epsilon, if necessary, we may assume, okay, A is less than C minus epsilon and C plus epsilon is less than B. Therefore, this interval completely lies in B. Yeah. Now again we use the LUB property. Now epsilon is positive and C minus epsilon is less than C. This is LUB. Therefore, what do I know? This is not an upper bound. Therefore, there exists an X in E. So that, so this is my C minus epsilon, C, and this is C plus epsilon and B. My X has to be greater than C minus epsilon, but remember X is in E, therefore X must be less than or equal to C, therefore my X may be somewhere here. Right? So that C minus epsilon is less than X, less than or equal to C. Right? Now X is in E, what does it mean? That is, AX is covered by finitely many things, therefore there exists an Fx, a finite subset of Y, so that the interval A to X is contained in I, maybe let us say, I used already I, so let J in F of X, so that AX BX, which is UX, UJ, oh sorry, AJ BJ, which is UJ. Right? But let's look at, I have A, I have C minus epsilon, C, C plus epsilon, and B. Right? Now let us look at C plus epsilon by 2. Right? Then what do you see? The interval, closed interval, A plus A to C plus epsilon by 2 is a subset of A to X closed union C minus epsilon to C plus epsilon. This is my X. This is covered by Fx. Okay, indexing set Fx, and this is covered by okay? But remember, this fellow is contained in Uj, J in Fx, and this fellow is contained in Ui. Right? Therefore, A to A plus C plus C by epsilon 2 is covered by Ui, where I runs over Fx union singleton I, maybe Fj singleton I. Remember, I chose my C to lie in, oh, I wrote it as AJ only. I'm sorry, then I could have done it as AJ here. Make it, therefore there is an, for each I, AI, AI, UI, and therefore this is contained in this is contained in union UI, IN, Fx and Uj. Therefore this is contained in UI, IN, Fx union singleton J. Okay, therefore what does it mean? This means C plus epsilon by 2 is in E. So pause, review, proceed. Please do not get lost with the notation change. That's why I keep saying notations are not important. If you understand what is happening, the concepts, the ideas are clear, you will not be intimidated or confused by the notation. Okay, but this is a contradiction because C plus epsilon by 2 belong to E and C is the LUB of E. That means C plus epsilon by 2 is less than or equal to C. This is a contradiction. Why did the contradiction arose? Because if C is not equal to B, then I was able to squeeze in something, right? Therefore our claim is correct. Okay, so pause, review, proceed. Now to complete the proof, this is the last claim. I claim B itself is in E. That means A to B is covered by finitely many. It admits a finite subcover. Yeah, that again the proof is exactly the same way. Start with the B. Now I will not write all the things. Okay, you should be ready. So there exists, again I will use a J. It's not the same J earlier. Okay, so that my B belong to AJ, BJ, which is UJ. You understand? Now AJ is strictly less than B. If necessary, again I can assume. Okay, let me assume A is less than AJ is less than B. Right? That will be of course less than BJ. This can I assume? If necessary, I can shrink it because my B belong to AJ, BJ. Okay, my A might have been here. Right? What do? I shrink this to make them think. Okay. I hope all of you follow this kind of stuff. I'm always little worried how many of you are following. Okay. Yes. Okay. Anyway, let us assume. Okay. Because these are subtleties, one should always think and look at it carefully. Anyway, so I am assuming, what am I assuming? A and AJ, and this is my B, and this is my BJ. Okay. Now since AJ, okay, belong to the interval AB, sorry, since AJ is less than B, in fact I don't even need that. Yeah, I don't even need that. Okay, since AJ, so forget whether AJ and A, the relative position does not matter. Since AJ is less than B, which is C, which is the LUB of E, I know there is an X in E, so that X is AJ is less than X, less than or equal to B. Now remember my X is where? Do you follow that? Therefore my A to X is covered by finite many AI, BI, I in f of X, a finite subset. Because since X belong to E, there is it A to X admits a finite subcover. Right? But no, let us look at what is A to B. A to B is A, AJ, X, B and BJ. Right? This is contained in A to X union AJ, BJ. But this is right? This is contained in union ai bi. I is the finite set of x, union uj. This is union uj singleton. Therefore the interval ab is again covered by finitely many uj's, right? Therefore b also belong to e, and hence the closed and bound interval ab admits a finite subcore. Okay, please go through the proof. Yeah, please go through the proof. In spite of the I and j I slightly change, okay, you should not lose track of what is happening. The proof is very simple. And remember, again and again I emphasize, it's time for you to master the LUB concept. Okay, I hope you enjoyed this lecture. Okay, go through the proof of compactness of AB again, and if necessary, go back to my connectedness proof, or you want to master completely, go back to my article LEB property. Yeah, okay, we will meet again.